Now let's review the law of conservation of energy. Remember that in a system, the total energy is going to be the sum of the kinetic energy plus the potential energy. If we derive the formulas, we're going to have then the total energy is going to be 1/2 of the mass times velocity squared plus mass times gravity times height. Okay? Let's remember how the total energy is conserved with this animation. Look that the total energy here is not changing, but the potential and kinetic are changing depending the potential of the position of the skater and the kinetic on the velocity the skater acquires. When the skater reaches the lower point, it has the maximum kinetic energy with the lower potential, and when the skater reaches the higher point, it has the maximum potential energy but the lower kinetic energy, or zero. So we are going to have that at this point the total energy, which is potential energy plus kinetic energy, where the motion hasn't started, the kinetic energy is zero. So we, at this point at the top, we're going to have only as maximum energy or total energy potential energy. While the skater is changing position, we're going to see in a moment, for example, like this. For example, now here, the total energy is going to be the sum of the potential plus the kinetic. When the skater reaches the lower point, the total energy, which is the potential plus the kinetic, at this point where the height is zero, we are not going to have potential, so we are only going to have kinetic energy. This is very useful because when we have to calculate the energy at intermediate point, we can compare the total energy at the higher point or at the lower point in order to get the rest of the information that we need to solve the problem. So let's check another thing. Now, the law of conservation of energy, but now on a spring. On a spring, we have to consider that the total energy is going to be, again, the kinetic energy plus the potential, but the potential is going to be divided in two parts. The potential because of the position and the potential of the elastic potential energy, elastic. So for a spring, we have to consider these two potential energies. In order to find the total amount of energy in a system, then we have to sum the kinetic plus both of the potential energies. Now look, as the spring is compressing, the potential energy increases. As the spring is stretching, the potential energy decreases. Look what is going to happen when it's stretching. The potential energy decreases and the kinetic starts to increase. In this case, we have a third option or a third type of energy, which is the elastic. If you see in the graph is the clear blue. So look how it changes. And the sum of these three is the total energy. In this case, this animation is considering the thermal energy. In most of the exercises, we are not going to consider thermal energy. But look how it changes. At the end, the sum of all the three energies is going to be the total energy. Well, now let's solve an example. It says a body of mass 4.2 kilograms with initial speed of 5.6 meters per second begins to move up an incline as shown in the figure. So look, here we have the mass and starts moving with certain velocity, and then the object is going to move up over the incline, but at the end of the incline we have a spring. So the problem says the body will be momentarily brought to rest after colliding with a spring of a spring constant of 220 Newton per meter. So it means that the object is going to move along this path, and when it collides with this, when it hits the spring, is going to be for a moment at rest, and then it's going to be pushed down by the string. The body stops a vertical distance of 0.85 meters above its initial position. Determine the amount by which the spring has been compressed. There are no frictional forces. Okay, so as I said, the object is going to move along this path until this height, which is 0.85 meters. So let's solve the problem. What is the information that we have? We already have the sketch, and then what is the information that we have? We have that the mass equals 4.2 kilograms according to the text of the problem. It says it's here. Its initial velocity is going to be 5.6 meters per second. And because the object is going to move from here to here until it stops, the final velocity is going to be 0 meters per second. Okay? We have also the spring constant, which is K, and it's 220 newtons per meters. And also we have this height that is 0.85 meters. So height equals 0.85 meters. So if we apply the law of conservation of energy, we are going to have that the total energy equals the kinetic energy plus the potential energy. The thing here is that because of the object is moving from an initial point to a final point here, we have to divide our analysis. First of all, we are going to calculate the energy at the bottom. We're going to calculate the total energy in this position, okay? So the total energy at the bottom is going to be total energy equals kinetic energy, which is 1/2 of the mass times the velocity squared, plus the potential energy. Now look, in this case, we have to consider that we have two kinds of potential energies. We have the potential energy due to the position of the object, but also we have the elastic potential energy. Okay? So the elastic potential energy is given by this formula. Okay? So we have to add both kinds of potential energy because we have a spring. So we have to add mass times gravity times height plus 1/2 of the constant spring times the displacement squared. So at the bottom, we're going to have 1/2 of the mass, which is 4.2 kilograms, and the initial velocity, which is 5.6 meters per second squared. Now, what happened to the height at this point? At this point, height equals 0. So all this term is going to be 0. And here, at this point, we don't have a spring. So this is going to be 0 too. So this is going to be plus 0, plus 0. So the total energy at the bottom is only the kinetic energy. Making the calculations is going to be 65 0.856 joules, but let's consider that we only have two significant figures, so let's round it. So the total energy at the bottom is going to be 66 joules. Now we have to consider the object when it comes at the top of the ramp. So the energy at the top is going to be total energy equals kinetic energy plus potential energy. And again, kinetic energy is 1/2 of the mass times velocity squared plus potential energy, mass, gravity high, plus the elastic potential energy, 1/2 of the constant of the spring, displacement squared. Now, what happens at this point? The object is going to stop for a moment. So at this point, velocity equals 0. So all this term is going to be 0. Now we have mass, which is 4.2 times g, which is 9.81, times the gravity, which is 0.85, plus the elastic potential energy, which is 1/2 of the elastic constant, 220, times displacement. But we don't know the displacement, so we let it like this. Okay? Simplifying this expression, we have that 4.2 times 9.81 times 0.85 is 35.02. I'm going to round it to two significant figures, plus 1/2 times 220, which is 110 x squared. Now we have two equations, this equation and this equation. So energy at the bottom equals 66 joules and energy at the top equals 35 plus 110 x squared. Now, if you see, we have like two equations, so we are going to equal the equations because these two are the same. So we're going to have that at the top has to be the same energy that we have at the bottom because the law of conservation of energy. So the energy at the top is 35 plus 110 x squared, and this is equal to the energy at the bottom, which is 66 joules. So if you see, now we have an equation with only one variable, which is x squared. So what I'm going to do now is solve the equation. I'm going to subtract 35 from both sides of the equation. So this is going to cancel, okay? And then I am going to divide both sides of the equation times 110. And now I can see that this cancels. And then we're going to have the x squared equals 31 over 110. And the root of 0.28 is 0.53 meters. So the amount by which the spring is compressed is by 0.53 meters.